Hi, my name is Leen, and in this video I would like to talk about the low power features of one of Renesas' newest microcontrollers, the RA2L1. In this block diagram we can see the RA2L1 group shown here on the right. The RA2L1 includes the ARM M23 CPU core with up to 48 MHz frequency. Operating from 1.6 to 5.5 volt, the RA2L1 is offered with flash sizes of 128 and 256 kilobytes. There are several communication interfaces including CAN, I2C, SCI and SPI. An extensive timer set consisting of 32-bit and 16-bit general purpose timers and two low-power asynchronous timers are also included. The RA2L1 has 12-bit ADC and DAC channels and up to 32 capacitive touch channels depending on the package option. Finally, the device incorporates elaborate safety and security features to complement the package. As I already highlighted in one of my earlier videos, the RA2L1 is packed with features. In this video I will detail with box number 1, the RA2L1 offers low power operation and is designed for ultra low power consumption. This device consumes an operating current of 64 microamps per megahertz in active mode and has a software standby current of 250 nanoamps with less than 5 microseconds fast wake up time. It has a flexible power architecture and several low power modes to achieve lower average power for multiple applications. Key in the flexible power architecture is the extensive clock tree of the RA2L1, including the ability to operate with either an external main clock oscillator or a variety of internal oscillators. Here you see the complete clock tree as is detailed in the user manual. However, the clock management has been vastly simplified in the user-friendly development environment. The configuration that is configured in this tool is the clock that drives the device immediately after startup. The clock source can of course be modified during runtime. A big advantage of the accurate internal oscillators is that external oscillators can be eliminated, saving both cost and board space. Please note that an external oscillator must be used if you wish to use the CAN peripheral. All RA devices support low power modes with operational flexibility that can dramatically reduce current consumption by allowing operation of a peripheral while keeping the CPU and other peripherals disabled. As an example, in sleep mode the core is gated and peripherals are available. In software standby mode the core is clock gated and most peripherals are data retained. In deep software standby mode, which is available in the RA6 series MCUs, the core and most peripherals are powered off. Here you see the typical power consumption of the RA2 series in various modes. The RA2L1 supports the unique feature of either operating with an internal LDO or efficiently with an external DC-DC converter. The DC-DC converter itself is internal. The disadvantage of using the DC-DC is that an external inductor must be connected. Here you see the different connections when powering the RA2L1 with the internal LDO or internal DC-DC converter. The additional components are highlighted, but the advantage is a power saving of approximately 40% in active mode. Here you see the power modes and power consumption specific to the RA2L1. The RA2 series has two types of low power modes, normal and sleep. Software standby mode is CPU clock gated and memory and peripherals are retained or stopped. Current consumption is lowest and wake up time to active mode is only 4.8 microseconds. Software standby mode also offers a snooze function that enables AD transition and data reception even if the CPU clock is stopped. The CPU will activate automatically only when necessary during snooze, for instance when the AD value exceeds a certain value. The snooze feature provides operational flexibility to dramatically reduce current consumption in applications that do not require the CPU to run code. Snooze allows certain peripherals to operate while the CPU and other peripherals remain disabled. Independent wake-up signals are provided for the data acquisition and data transmission peripherals. The aforementioned power consumption savings can easily be demonstrated with a low-power application app note, an example project provided by Renesas. It can be downloaded from the link on this page. The example project starts up in high-speed on-chip oscillator mode, active mode, and is subsequently possible to step through the different power modes including sleep and standby mode. This is done by making a long press on button 1 of the evaluation board. Sidestepping into the sleep and standby modes is done by making a short button press. The power supply makes use of the internal LDO. Such as so. Here you see the typical power consumption figures measured directly on the board. Slightly higher values are seen as the RTT communications are running with the development PC. Here you see the typical power consumption figures measured directly on the board. In this case, the RTT comms are disabled. I will now demonstrate the actual example program. Here you see the device immediately after restart. The LED is flashing to indicate active mode, and you see the power consumption goes up as a result. The RTT client is running to indicate the power state that the device is in, and if you press the button, in this case the device switches to middle speed on-chip oscillator mode. Another long press brings the device into low speed on-chip oscillator mode, and you now see the value of the power consumption dropping to 0.66 milliamps. That's because the RTT communications are still running. If I disable the RTT communications, then the power consumption drops down. Here you see the RTT communications trying to reconnect, but that's not possible. But the device is in high-speed on-chip oscillator mode. Power consumption is approximately 5.1 milliamps. Giving a long press brings the device into middle speed on-chip oscillator mode. Power consumption now drops to approximately 1.16 milliamps. Giving another long press brings the device into low speed on-chip oscillator mode, and now you immediately see the low power consumption dropping down to 0.05 milliamps approximately. The board is now in low speed on-chip oscillator mode in sleep mode. The chip is now in software standby mode, the lowest power consumption, and automatically times out after 5 seconds and goes back into low speed on-chip oscillator mode. This concludes the demonstration of the example code. Download the low power example and implement these features in your next application. In closing, I would like to thank you for your attention, and if you have any questions or recommendations for future videos, don't hesitate to contact me on this address. Thank you for your time.